Hey guys, so this is my first video, and today I'm going to explain about the reactions of monosaccharide. So let's get started. So first we'll know about what is monosaccharide. First we'll know about what is monosaccharide. Monosaccharides are molecules having only one actual or potential sugar group, and they cannot be hydrolyzed further into smaller units. So monosaccharide is a type of carbohydrate, and carbohydrates when classified according to the number of sugar groups present can be classified into monosaccharides, which we are discussing today, and disaccharides, oligosaccharides, and polysaccharides. Also, on the basis of number of carbon atoms, they are classified into triose, 3 carbon atoms, tetrose, 4, pentose, hexose, and heptose. And on the basis of presence of aldehyde or ketone group in the sugar, they are classified into aldose and ketose. Aldose has aldehyde, ketose has ketose. So these are some examples. Aldoses, in triose, aldoses is glyceraldehyde and ketose is dihydroxyacetone. Tetrose, aldose is erythrose, ketose is erythrulose. Same with pentose, hexose, and heptose. Now, first reaction we'll be discussing is amino sugar formation. So, in amino sugars, the amino groups are substituted for hydroxyl groups in sugars to give rise to amino sugars. And mostly the OH group present in the second carbon of hexoses is replaced with the amino group. Example is glucose to glucosamine. The amino group present in the sugar may be further acetylated to form N-acetylated sugars. Example is N-acetyl glucosamine, and they do not show any reducing properties. Now, clinical importance of amino sugars. Glucosamine, it is present in hyaluronic acid and heparin. Heparin is responsible for coagulation of the blood. Galactosamine is present in chondroitin of cartilage, bones, and tendons. Manosamine is present as constituents of glycoproteins. So this is the glucose having a amino group in the second carbon. Glucose is actually a hexose, so glucosamine will have a amino group in the second carbon, and this is an acetyl glucosamine in which the amino group, it is acetylated, that is, it reacts with acetic acid. Now, osazone formation. In osazone formation, the reducing sugars react with excess of phenylhydrazine under boiling temperature at mild alkaline conditions to form osazone. Now, glucose, fructose, and mannose, which are 3 sugar molecules, they differ in the spatial configuration of the carbon atoms, but all of this difference is masked because after the formation of the respective osazones, because the osazones of glucose, fructose, and mannose are similar broom-shaped structure or needle-shaped structure. Osazone formation helps in the identification of sugars present in various biological fluids like urine and blood, and osazones are insoluble in solvents. Now, third reaction is indiol formation. In indiol formation, under alkaline conditions, carbohydrates with sugar groups tautomerize to give indiols. Indiols consist of 2 hydroxyl groups connected to double bonded carbon. Indiols are highly reactive reducing agents in alkaline medium, and glucose in reactions in which the sugars are converted to corresponding sugars by passing through an intermediate indiol stage, come under the classification of Lobre-de-Braun-Eckenstein reaction. One such example I have written here is glucose. It gets converted into fructose and mannose by passing through the intermediate 1,2-enediol form. And next is the Benedict's reaction. It is mostly undertaken to it used to be mostly undertaken to check presence of glucose in urine or to detect the condition called glucosuria, but now it is no longer used. So what happens in Benedict's reaction is, I've drawn here. So there it's like a loop-like structure, as you can see. So this is the sugar molecule. It forms indiols. Now after formation of indiols, mostly only reducing sugars will form indiols. So if the sugar is non-reducing, it will not form indiol, and hence it will not undergo the Benedict's test. So now the reducing sugars, they form indiols. They undergo formation of indiol by tautomerization. Now indiols can either oxidize to form sugar acids, or it can get reduced under the Benedict's reagent. Benedict's reagent consists of sodium citrate, sodium carbonate and copper sulfate. So it gets reduced in the presence of Benedict's reagent to form copper hydroxide, which is a yellow precipitate, which later forms copper oxide, which is a red precipitate, and it is also used as a test to find out whether the sugar is reducing or not, or it will form, it is reducing or not. If it is reducing, it will give the red precipitate in Benedict's reaction. Next reaction is reduction to alcohols. So in reduction to alcohols, carbohydrates combine with hydrogen to form sodium amalgam. Carbohydrates combine with hydrogen in the presence of sodium amalgam to form alcohols. Now sugars with aldehyde groups called aldoses will form only one alcohol, but sugars with ketone group or ketoses will form two alcohols. This is because of the presence of two asymmetric carbons in ketoses. And here are some sugars and their corresponding alcohols. So glucose will form sorbitol, mannose will form mannitol, fructose will form sorbitol and mannitol both, galactose will form dulcitol, and ribose ributol. Now significance or functions of alcohols. So sorbitol, mannitol and dulcitol, the combination of these three are help in the identification of bacterial colonies. Sorbitol and dulcitol with aging get accumulated in the islands, present in our eyes, like in front of the eyes. Eyes consist of islands in them. It gets accumulated there, leading to fogging of the lens, which is known as cataract. It happens with age. In the cases of diabetic patients, the formation of sorbitol and dulcitol is more, therefore it might cataract mostly happens a little earlier for them because of more glucose levels, hence more formation of sorbitol and dulcitol. And mannitol helps in reducing intracranial tension by forced diuresis. Diuresis is removal of fluid from the cranial cavity so that there's no tension in the cranium. Now dehydration. In dehydration, monosaccharides react with concentrated sulfuric acid to undergo dehydration by removal of 3 molecules of water, and in this process they'll form furfuryl derivatives. So hexoses undergo dehydration in the presence of concentrated sulfuric acid, denoted as H+, and removal of 3 molecules of water to form hydroxyfurfural or 5-hydroxyfurfural. And pentose will undergo dehydration to form furfural. Molish test. Now this furfural derivatives combine with phenolic compounds to give colored products. This is the basis of Molish test, and Molish test is a general test of carbohydrates. So when carbohydrates dehydrate to form furfural derivatives and their furfural derivatives combine with phenolic compounds, they form a purple ring-like structure as shown, hence proving that they are carbohydrates. Oxidation of sugars. Under mild oxidation conditions, that is hypobromous acid, the aldehyde group is oxidized to carboxyl group to produce aldonic acid. Now, in certain cases, this aldehyde group is protected and the molecule is oxidized. Now, the OH present in the last carbon becomes carboxyl or COOH group, leading to production of uronic acid. Example is glucuronic acid. So in this figure you can see gluconic acid, the first aldehyde group is oxidized, and glucuronic acid, the last is oxidized because this is masked, it cannot be oxidized. And now last is under strong oxidizing conditions, that is nitric acid and heat, the first and last carbons both are simultaneously oxidized to form dicarboxylic acids or saccaric acids. So example is glucosaccaric acid, in which both first and last carbons are oxidized. Now esterification. The hydroxyl groups of sugars are esterified to form acetates, propionates, benzoates and phosphates. So we can see here the hydroxyl group, like over here in glucose, the hydroxyl group present in the in the first carbon atom is oxidized, is esterified to form glucose 1-phosphate or choreester. Similarly here in the last carbon of hydroxyl group of sugars are esterified to form glucose 6-phosphate, which is Robinson ester. Now sugar phosphates are of great biological importance, and one such importance is that metabolism of sugars inside our body, it starts with phosphorylation, and two intermediate of this glucose metabolism are the choreesters and Robinson ester, which is shown here, and these are esterified form of sugars. Now last reaction is formation of deoxy sugars. So as the name suggests, deoxy, this is basically removal of oxygen from the hydroxyl group of sugars, leading to formation of deoxy sugars. And they don't have any reducing properties and they don't form osazones. Example is L-fucose, which is present in blood group antigens and many glycoproteins. And most famous deoxy sugar is deoxyribose, which is present in DNA, deoxyribonucleic acid. And biologically important deoxy sugars are 6-deoxy-L-galactose and 6-deoxy-L-mannose. So that is the end of this video. I hope you liked it and understood the different reactions of monosaccharides. Make sure to like the video. I'll see you in the next video. Bye.